Good afternoon, everyone. We'll continue today our lecture on the recently introduced laws, Faraday's law and Lenz's law. Uh, okay, so here we have an example that we need to do. In this example, we have the circuit shown below consists of a 3-volt, 1.5 watt light bulb. So this is the maximum voltage that can be applied to achieve the full brightness. Connected using ideal wires with no resistance, conducting bar with no resistance is connected to those wires, and it can slide on those two wires. Right now, it's been pulled at the velocity in the right direction of v through a uniform magnetic field, 0.1 Tesla, that is pointing into the page. Where the width here, or as you can see in the figure, 10 centimeter, which is also the length of the bar within that circuit, is 10 centimeter, and the current, and L is the length. L is the length of this wire from here to here. So the question is asking for the speed that should be applied in order the light bulb can achieve full brightness. Okay, so let's start. Okay, so here we have those two wires, and then we have a light bulb here, 3 volt, 1.5 watts, and then there is a bar that can slide. This bar has been pushed to the right in this direction. I have the magnetic field pointing into the page, as you can see. Uniform magnetic field. I have the length here. This is 10 centimeter, right? And this is the length. So this is W. This is L. And we need to calculate the velocity V, such that this light bulb is achieving full brightness, which means electromotive force is 3 volts. Okay, so electromotive force is 3 volts. And then we know that the electromotive force magnitude is d phi over dt. And here, in this case, we have the motional electromotive force because the area is being changed. The area is changing where the magnetic field is uniform and steady. So in this case, I have this d a dot v. right? Then, as you see, I have the magnetic field perpendicular on the area here. So the dot product is going to be 1. The cosine theta is going to be 1 because I have the normal unit vector of this area parallel with the magnetic field. So I have here the electromotive force equals to dA over then this is going to be dA over dt times B, right? So the electromotive force equals to d over dt for W times L, and this is all multiplied by with the magnetic field. However, as I said, B here is constant, W is constant, so here this d over dt is for W times L. However, W is constant, then the electromotive force, let me move B to the front here so it does not confuse you. D over dt omega times L, or electromotive force equals to D times W constant goes outside, so I end up with dl over dt. Now dl over dt is my speed v, then equals to dw v. And in this case, v will be 3 divided by 0.1 times 0.1, which one of them is the length, and the other one is the magnetic field, 0.1 Tesla, which means V equals to 300 meters per second. Any questions so far? V is the dl over dt, the difference in distance divided by the difference in time. Yes, this is the magnetic field, 0.1 Tesla. This is the W, which is the width of the wire here, 0.1 meter, 10 centimeter, 0.1 meter. Any other questions? Okay. Now the second part of the question is calculate no, because if you recall, when it comes to the area, you're talking about the area with the angle between the magnetic field and the normal unit vector on that area. Yeah. Okay, so the second part of the question is, what is the force exerted on the moving bar? Now, when it comes to the force, you need to understand that so what's happening is the following. Because you pulled that bar to the right, you increase the area. Since you are increasing the area, you will be increasing the flux that's going into the screen, which means the magnetic field is increasing into the screen. Now, the loop will generate an opposing magnetic field that opposes this increase, which means it will be pointing out of the screen like this. And now this magnetic field that is pointing out of the screen will, based on the right-hand rule, will result into a current that is going counterclockwise. So now the current will be flowing in this direction. And this current, or this induced electromotive force that resulted with this current, is the one that is responsible for the magnetic force that we are seeing right here, that is opposing the other force that you have applied to generate the bar, to move the bar to the right. So in other words, this magnetic force will always look like a resistance to you. So if you are to hold this bar and try to slide it left and right, you will always see a resistance toward your motion. This resistance toward your motion came from the magnetic force induced by the opposing magnetic field. Due to the induced electromotive force in that loop. And this induced electromotive force resulted into this current flowing, and this current resulted into the magnetic force. Okay. So now we need to calculate this force. So what we know is now F A applied equals to F B, and this equals to I L cross B. Now the L that I'm talking about is this L, the bar. If you recall, the W that we had, which was 10 centimeter, is the L in this case. The B is the magnetic field, and the current is the resulted current from this closed path. So remember we said that we had here 3 volts and a power of 1.5 watts. So at 3 volts, we can find the current. So power is the electromotive force I, which means I is P divided by the electromotive force, and this is P is 1.5 divided by 3. I is 0.5 ampere. I is 0.5 ampere. Back to the magnetic field here. Sorry, magnetic force. So I know this is a magnitude. There's a magnitude here. So I know F APP now equals the current I. L is the W. Now the magnetic field is right perpendicular on the bar, which means this is going to become ILB. Why? Because it's perpendicular and the angle here is sine 90 degrees equals to 1. So FAPP, again, this is magnitude because FAPP is equal in magnitude, opposite in direction. So you have to be careful. So they are in magnitude, they are equal, which means that FAPP equals to the current 0.5 times the length, which is 10 centimeter, times the 0.1 Tesla, and FAPP equals to 5 power minus 3 Newton. Any question? Okay. Here the L is different than the L we used before. Here my L is the length of the bar. So here my L is this length of the bar. This is my L. Here, now this is my L. And L here is a W. The magnetic field, it's already there into the screen. The green crosses are the magnetic field into the screen. The orange is the opposing magnetic field. Now, the current and the magnetic force are related to the opposing magnetic field. This magnetic field that goes into the screen is an external magnetic field that already exists. When I move the bar to the right, I made an increasement in the flux into the screen. This increasement of the flux into the screen resulted into an increased magnetic field pointing into the screen. At that point, there will be now an opposing magnetic field opposing this increase in the magnetic field. This opposing magnetic field will result into an electromotive force and a current. We saw that the current will be going up this way, and if you use the right-hand rule, the magnetic force if you go up, pointing toward into the screen, you will see that the magnetic force will be opposing the applied force. So FB here is opposing the applied force. Now, let's go to this question where we again been given uh, a, the same setup. Instead of the light bulb, we have a resistor here. Now, if you apply a force FAPP to move the bar to the right with a constant speed of V and a power input at the resistor of P, imagine that the force is increased so that the constant speed of the bar is doubled. So the velocity or the speed here has been doubled. Under these conditions, what are the new force and the new power generated at the resistor? So we have, as you can see here, bar being pulled to the right with the force FAPP. Then what's going to happen to the power and to the force if the velocity of the speed has been doubled? So this is the same tool. So we have FA applied, we have the velocity V. This is going to result into a magnetic force. We have the magnetic field also entering. So from what we have derived earlier, we can say that the electromotive force magnitude equals to B W. My W here is this L, B, L, and the speed is V, right? So now again, this is going to result into a current that's moving counterclockwise. This way. And that's why the magnetic force is pointing to the left, opposing the force applied on the bar. But what I know that the electromotive force here equals to R Ri, that equals to magnetic field B L V, the speed. Then I know this is going to give me I equals to the magnetic field B L V divided by R. So this is the relationship now between the speed and the current. I'm trying to derive the relationship that I need in order to relate everything to the speed, because my speed is going to be doubled. I want to see what's going to happen to the power. I also want to see what's going to happen to the force. So in this case, if this is the current, I know that P equals to RI squared. So this is the relationship now between the power and the current. Also, what else I can use? I can use the magnetic force FB equals to ILB. Where did I get this one from? Well, this is the magnetic force from IL vector cross B vector cross B vector. However, the magnetic field is perpendicular on the bar. That's why the L magnitude, B magnitude, sine theta is 1. So I have sine theta equals 1 because B is perpendicular on L, and the direction due to the right hand rule, FB is pointing to the left. So now I know that FB equals to ILB. So at a steady state, when my velocity or speed becomes constant, I have FABP equals to FB in magnitude. So when the V is constant, I have FAPP equals to FB in magnitude. Then I can use the derived formula here. So now let's look at what's going to happen to my power and my force. If I put V as 2V, what's going to happen to the current? If the speed is doubled, then the relationship is linear between the current and the speed, and then the current will be doubled as well. Okay, that's great. So if I say here, if I substitute 2V in V, this way my current, so let me say here, let me put it this way. I nu equals to B L times 2V old divided by R. This means I nu will be 2I old. Now, if this is P old, if I put now P new equals to R, I new, which is 2I old, squared, this is going to P new will be 4 R I old squared. So this is P old. That's why P new is 4 P old. Now what about the force? If I substitute now FB new with 2I old LB, then FB new would be 2 FB old. So in this case, we notice that the force will be doubled because it's linear. The relationship between the force, current, and velocity are all linear. However, the power will be 4 times because it will be 2 times squared. Okay. Any questions so far? Okay. So let's move on to the next. Okay. In this question, as you can see, we have 4 cases of loops. Okay. What was the answer? It was B. F is linear, will be doubled, and the power will be 4 times. B. Yeah. Okay. Now, if we look at this slide, we have several cases of loops that exist in a magnetic field, and we would like to evaluate each one to understand if we are getting induced electromotive forces or no. Okay. So here the question is asking about the motional electromotive force. We will be mentioning all kind of induced electromotive force that do exist. So let's start first with the case A. In A, as you see, we have a sliding bar that you can move to the right or to the left. You can slide it. Now it's been pushed in the right direction. Now, when you pull it to the right direction, what you will be doing? You will be shrinking the area, which basically means that you are reducing the flux, and as a result, the magnetic field will be decreased. The magnetic field will be decreased and this direction into the screen. So if it's decreased into the screen, which basically means will be in the opposite direction, there will be an opposing magnetic field trying to compensate for this loss. So the opposing magnetic field will compensate for this loss, and that's why he will be going into the screen. Why? Because the decrease is happening out of the screen. The opposing magnetic field will go into the screen trying to compensate for this loss. He will resist any change to this magnetic field. So when the opposing magnetic field go into the screen, based on the right-hand rule, he will generate an induced electromotive force such that the current is going clockwise. So the current would be going in this direction. Yes, yes, it is inducing electromotive force. So the magnetic field, opposing magnetic field, will be pointing into the screen, and then based on the right-hand rule, the current will be going in this direction. So there will be an induced electromotive force. What about case B? In case B, we have a uniform magnetic field that has a loop going in this direction and this velocity from left to the right. So there are no changes in the flux. The magnetic field is uniform everywhere in this region. Doesn't matter how you move this loop, you will not get, if you maintain the same orientation, of course, such that it is in the same plane, but if you move it this way or that way or up or down, based on the type of this magnetic field, there will be no variation in the flux. So let's talk about this case in specific, moving from left to the right in this speed. In the existence of this uniform magnetic field, there will be no variation in the flux, which basically there will be no induced electromotive force. So case B has no induced electromotive force. What about C? C has the loop that is rotating. Yes, it is just moving, but there is no variation in the flux. No change in the area or no change in the magnetic field. That's why there will be no variation in the flux. Now, case C is a loop that is rotating in the existence of the magnetic field. This rotation is going to change the effective area. The effective area that this magnetic field is seeing, which basically means that a motional electromotive force will be induced because of this rotation. Once it rotates, then the area that the flux is going to vary because of the dot product between the normal unit vector of this area and the magnetic field, which means the total magnetic field that is penetrating or crossing this loop will be changing, and that's why I have a time varying flux. And in this case, yes, I have an induced electromotive force, and it is from motional electromotive force. Last, because the area is changing, if you, for example, look from here, you're gonna see, I will now redraw this. Let me draw this in a, so the magnetic field will be pointing out of the screen. And this is the loop that I would be seeing. The rotating loop, but this is the moment, let's say this is the T0. At T equal 1, now this loop is going to look bigger. The area is going to look bigger. At T equal 2, it's going to look like this. all of them at t equal 4, for example, is going to be completely perpendicular. And then we'll start decreasing again and then increasing and so on. So that's what's happening. So as you can see here, the area is 0. Why? Because the loop is completely in parallel with the magnetic field. So there is no area. Then this loop will start rotating and the area will start to increase. Then it becomes maximum. And then we'll rotate again till it goes to 0 and so on. So with this motion, you will see that the area is varying between 0 and maximum. Is this clear? Okay. Yeah. Go ahead. Go ahead. It depends. It depends. It depends. If the magnetic field is uniform, which means the magnetic field is the same everywhere, then you're not going to see a changes. However, I was going to come to this case in the case number D. In case number D, if you go to D, I have a wire. This wire has a current going up. And then I have a loop that is moving in a speed this way. This speed is parallel with the wire. Now, if you recall the magnetic field for such a case, B equals to mu naught I divided by 2 pi r. So if I take the magnitude just to make it simpler here, I know that the magnetic field to the right of the wire will be pointing inside. So right here. But what I am going to do, I'm going to show you the magnitude I will define the strength of the wire in terms of the field density. So here is entering. Then it will be a bit less. The further I go, the weaker the magnetic field becomes. Now, if I go parallel to the wire this way, my loop is not going to see any variation in the magnetic field. There will be no variation in the flux. However, if I go in this direction, then I will be seeing a variation in the flux. Why? Because I'm coming from a weaker magnetic field toward a stronger magnetic field, then definitely I will see a variation in the flux. But when I was going parallel, going up, when I was going up, I can't see any variation in the flux. I'm having the same magnetic field in my loop. But if I move to the left, closer to the wire, then yes, I'm coming closer to the stronger magnetic field. Then I will be seeing a difference in the flux, and I will be seeing a variation in the flux. The same thing if I go this way. I'm going toward, I'm going further from the wire, which means I'm going in the direction of a weaker magnetic field, coming from a stronger magnetic field to a weaker magnetic field, then yes, I will be seeing a variation in the flux. But right now, only with moving parallel, then I will not be seeing any variation in the flux. There won't be any induced magnetic force. No, now it's not. It is not going. Okay, it's not going in rotation for case B, D. It's going parallel. Okay. So you need to understand the concept. As long as you have a variation in the magnetic field or a variation in the area that you are doing a cross product with, then you will be having a variation in the flux. Once both of them are not varying with time, then you have no electromotive force. Okay. Any other questions before we move on? Now let's look at this question. This is another example of what I was just referring to in the D example. Now, in this question, we have a loop, a circular loop of wire falling toward a wire carrying a current to the left. What is the direction of the induced current in the loop? Yes, C and D, or there is E, more than one of the above. But yes, only C and A, only C and A are the ones that induce electromotive force. Okay. No, the answer is A and C. A and C. Okay. Now for this loop, for this circular loop that is falling in a speed toward the wire, basically it is coming from a weaker magnetic field to a stronger magnetic field. Why? If this wire, as you can see here, based on the right hand rule, if you look at the right hand rule, you will see that the magnetic field is pointing into the screen at this side, at the upper side of the wire, pointing into the screen. The closer I come to the screen, the denser those magnetic field becomes, which means stronger magnetic field, right? So if this loop is falling toward this wire, it is coming from a weaker magnetic field into a stronger magnetic field. All of them are pointing into the screen, which means that the magnetic field is increasing, pointing into the screen. Then there will be an opposing magnetic field pointing out of the screen, and the current based on the right-hand rule will be counterclockwise. Okay? Now, what's going to happen to the magnetic field below the wire? If the magnetic field above the wire will be pointing into the screen, for the opposing magnetic field. So the right-hand rule here is between the current and the opposing magnetic field. That's why we have the minus in Faraday's law, because we're referring to the external magnetic field, the opposing magnetic field. The right-hand rule is applied on the opposing magnetic field. The opposing magnetic field is the one that defines the direction of the current. Now look what's going to happen below the wire. It will be the opposite, right? The magnetic field will be pointing out of the screen. So if this loop now continues to go below that wire, the magnetic field will start to decrease into the screen, which basically is going to result into a magnetic field opposing coming out of the screen. So the current direction will not change. The current direction between moving from above the wire to below the wire will maintain the same direction. Okay? Go ahead. Because the magnetic field was generated by the wire was pointing into the page, into the screen, increasing in the direction into the screen. What I care about is the direction of the change. So it was increasing into the screen, was increasing onto the screen, which means the opposing magnetic field will be pointing out of the screen. Based on the right-hand rule, pointing out of the screen, I have counterclockwise the current in the loop. So at the beginning, you look at the magnetic field and you see how is it changing. Is it increasing in the direction it's pointing to? Then the magnetic field will be opposing this increase. If it's decreasing but pointing into the screen, then the magnetic field will be pointing into the screen as well, but increasing to oppose the decrease that's happening into for the magnetic field. No, you use the thumb for the wire. If for the wire, for defining the magnetic field of the wire, of the straight wire, you use the thumb as the wire. But for the loop, you use the thumb for the direction of the magnetic field, and the fingers for the current. Okay, so let's move on to the next slide. Here, what we have explained earlier in terms of the loop rotating is basically what's happening in the generator. So as you can see here, I have a magnetic field that is crossing this loop, and this loop now is rotating. By this loop rotating, it will result into a change in the flux. Now, but right now, if I am to take a cross section, just to show you the cross section, if I am to look from here, then I would be seeing the loop like this, and the magnetic field like this. However, it is rotating around this axis with the omega this way. So it is rotating such that the area is increasing. It is rotating such that the flux is increasing in this direction, or the magnetic field is increasing for that area because the area is increasing in this direction. Basically, this means the opposing magnetic field is going to be in the opposite direction, and based on the right-hand rule, the current is going to enter at the top and come out of the screen at the bottom. If you look at the current, you will see that what we have concluded was correct. Yes, the current is entering at the top and leaving at the bottom. Okay, now the magnetic field, as I said, here the magnetic field is increasing in this direction of the loop, right? This is the loop. Remember, I always take the dot product. So what matters to me are the components of the magnetic field that are perpendicular. And the more I turn, the greater those component becomes, right? Is that clear? Because I'm taking the dot product. The dot product means here, I'm only interested in the components of the magnetic field that are perpendicular on my loop. So if this is the magnetic field that is increasing in this direction, then the opposing magnetic field would be going in this direction. And now if the magnetic field is opposing in this direction, use the right-hand rule, the current basically is entering from the top, leaving from the bottom. Okay, that's good. right when it reaches right to the maximum, and then once it's continue to rotate, now the current is going to be flipping, because now I reached the maximum and now there is no more anymore. I will now going into decreasing the flux and so on. But that's why they have the brushes, right here, as to always maintain the direction. Well, there is no one. It's not only one loop in the generator. There are several of those loops. So there are many of those loops. But anyway, so this is what's happening. This is how the current or the induced electromotive force is generated using the loop. So let's continue with the remaining slide before we stop. We have only one slide left. Okay, and so here we have an example. We have a coil that has an area of 2 meters squared. It rotates in the existence of a magnetic field of 9 to the power minus 3 Tesla with a frequency of 60 hertz. How many turns are needed to generate a peak voltage of 170 volts? So in this problem, this is the same problem of what we have seen, the loop that is rotating in the existence of the magnetic field. So we know the area is 2 meter squared. We know the magnetic field is 9 to the power minus 3 Tesla. We know the electromotive force is 170 volts. We know the frequency is 60 hertz. We need the number of turns. Now, if you recall the electromotive force, we said it equals to minus for the d phi over dt. This is correct for one loop, but if I have more than one loop, I have to put n before. So basically, the number of the turns will increase the amount of the electromotive force or the amount of generated magnetic field, and this is the effect of several turns of the current going through. So in this case, if I am to start with the flux, and I know that the flux equals to the B dot A, right? Which basically gives me as B A cosine theta, where theta is the angle between the normal unit vector of the area and the magnetic field. So this is phi. If I want to take the derivative of phi with respect to the t, it will be d phi over dt equals to also d over dt for b a cosine theta. Now, if I take the area as constant and what's varying is the theta, the cosine theta, then I can take the b and a outside. So this is d phi over dt equals to b a d over dt for cosine theta. This is going to result into d phi over dt ba, the derivative of the function, which is minus sine theta d theta over dt. Okay, so now what is the d theta over dt? D theta over dt is indeed the omega, the radial frequency. And we know the radial frequency is 2 pi f then this means d phi over dt equals to minus b a sine theta times 2 pi f. Now, if I take this d phi over dt and substitute it here, and the EMF equals to minus n, omega is the radial frequency, radians per second. Radians per second. How many radians per second I do when I go in a rotational motion? The amount of the angles that I elapse per second. Okay, angular velocity. So if I go back now to this, I have EMF equals to minus n d phi over dt. Then I can here substitute. So I have EMF equals to minus n, right? d phi over dt. I will write it in a different color. So I times minus BA sine theta times 2 pi f. This means EMF equals to NBA sine theta times 2 pi f, or N equals to EMF divided by BA sine theta times 2 pi f. Omega is the angular frequency. Yes, that's what we said. N has to go here because the electromotive force will be increased. Okay, so the best case scenario is when theta equals to 90 degrees and this becomes 1. This is the best case scenario. And in this case, n equals to 170 divided by 9 to the power minus 3 times 2 times 2 pi times 60 hertz, and the answer is n equals to 25 hertz. No, we don't know. We will assume that the maximum is when theta equals to 90 degrees. N is physically, we will use as N as a physical number. Once I have this coil with this number, that's it. What matters then is the theta, the angle. Angle can be changing based on the rotation. Okay? Yes. Any other questions? Okay, I will. So I'll see you on Wednesday.